talk about Bitcoin and quantum computing. The first reason we decided to do this talk instead of touching other topics is that we are feeling like there is a new scam coin narrative incoming right now. You know that periodically you have this function. I used the Rust so that he is happy. So you have for reason in R print Bitcoin is doomed because reason buy my scam coin now, and R is a set of different stuff from GPU mining to global warming to high fees and now to quantum computing. There is a new wave of terror. Quantum computing is coming, Bitcoin is doomed, so please buy my shitcoin now. This is typical. It's not the first time we see this kind of marketing tactics, so it's okay. But since now is touching a topic which is characterized by a very high information asymmetry, we thought it was particularly interesting to try to put some information in the right place. The second reason a Bitcoiner should be interested in Bitcoin and quantum computing at all is in order to fight an obvious case of Gell-Mann amnesia effect. What is Gell-Mann amnesia effect? So as Bitcoiners, how many of you are into Bitcoin since at least a couple of years? Raise your hands. So, okay, not everybody, but a good part of the group here was supporting or working on Bitcoin for a while, and we had to go through this blockchain hype. Luckily, it is almost dead. It's basically already dead in the USA. In Europe, the death is coming because there is some cultural lag. But basically, 2 years ago, if you were talking about blockchain, your startup evaluation was 10 times more. If you were talking about blockchain as an innovation manager in a bank, your career was getting a big boost. Now people look at you like a snake oil salesman, which is what you are actually. So what the characteristic of the blockchain hype are a huge terminological ambiguity, a lot of extraordinary and completely unbacked claims, like blockchain to clean the oceans, blockchain to stop climate change, blockchain to trace food into the supermarket, blockchain for fighting the exploitation of labor, whatever. Also, you have famous incumbents using a very dishonest marketing. So it's not that since there are famous people with very big corporations, you can expect some kind of consistent scientific exposition of what they are doing. There is a lot of marketing. Basically, what you have in blockchain hype is 99% of noise over signal rate. We already faced that. And what is Gell-Mann amnesia? Gell-Mann amnesia effect is when you read a newspaper about something you know very well about. You understand that the journalist is just making stuff up. Nothing makes sense in what you're reading because you're an expert, so you know that that doesn't make any sense. But then you turn the page about something you don't know as well, and you completely forget what you thought about the journalist as a group, the page before, and you start again to believe. I mean, this is famous people. This is a professor. This is an innovation manager. I'm sure they know what they are talking about. They are reporting honestly the things. Gell-Mann amnesia is the fact that you forget your skepticism after the sources you're reading have been proved dishonest or completely incompetent. So I think that Bitcoiner may have a Gell-Mann amnesia effect about other hypes which are not blockchain, but which are behaving pretty similar. The quantum computing hype, I mean, many technology hypes. We can talk about artificial intelligence, IoT, and whatever. Most of these buzzwords are characterized by the same things. A very huge terminological ambiguity, a very dishonest marketing, extraordinary claims, like about quantum computing. You can find articles online like quantum computing will end free will, quantum computing will any kind of extraordinary claim Quantum computing can do that, of course. And it's still, my thesis tonight is that if we maintain the same level of skepticism, we can try to analyze through the same rigorous and critical lenses also this other buzzword, since we already experienced it in Bitcoin, to analyze critically the blockchain buzzword. Of course, I mean, now you can ask, I mean, what do you mean? You mean that these people, so huge, reputable, rich corporation, may be that dishonest or incompetent about this topic? I mean, Google is saying that quantum computing will change everything. The same goes for IBM, and the same goes for Microsoft. So, thinking about what we have seen in the blockchain industry, can we really imagine that these people may be dishonest in marketing? Well, yes. Yes. Hell, yes, we can. I think we definitely can. The fact that there is no authority principle here. The fact that somebody rich and famous and big is making some claims doesn't make these claims more believable or more reputable. So let's move to another reason. Another reason to discuss quantum computing and Bitcoin is because, except for scam coin promotion and except for big corporation marketing buzzwords, there are also some serious discussions right now into the Bitcoin community about quantum computing as an hypothesis, as a possible scenario, mostly because of a general let's say, mood of going back from the idea of using Bitcoin in a pay-to-hash mode, so pay-to-public key hash, pay-to-script hash, pay-to-witness public key hash, to the old mode of paying directly to a cryptographic public key. This is for several reasons. There are like, you can read from Peter Willa, SIPA, a lot of discussions about taproot and graphroot. There are 7 applications in Lightning Network and in CoinJoin and in advanced multi-sig in which people share the master public key. So the fact that, I mean, there is this myth that we will try to debunk, that Bitcoin is protected significantly from quantum computing because we don't pay public keys, but we pay the hashes of public keys, and so we should keep it that way, while there are a lot of reasons right now to actually switch more to a public key based kind of interaction and not a hash based kind of interaction. So this discussion is real. If that kind of movement is risky, we should not do that. And we should give up all the cool things that we can do having this kind of strategies. If the risk is not real or not immediate or not serious or not important, not consequential or not probable, then we can experiment with this feature with more open mind, let's say. There is the last reason, which is historical. It's a tribute. So tonight I'm paying a tribute to the beginning of the scamming career of a famous scam coin promoter that started basically the first investment he proposed to the public in the Bitcoin community was actually a quantum computing scam, and he proposed that with a talk that was entitled exactly like this, like Bitcoin and quantum computing. So this talk I'm giving tonight is a tribute to a master scam coiner that I think in front of attendee more or less like this made the same kind of talk in order to promote his first investment scheme. Of course, I will not name this person because it will not be elegant or fair, so I will not name it, and I will just go on with what it. Oh, sorry, no, I don't know what it is. Sorry. Okay. So let's enter the merit of the topic. So we have to discuss 2 things here. I will discuss very quickly some points about the security model of Bitcoin, and then I will focus more on quantum mechanics and quantum computing in general, because I assume that most of the people here are, as you said before, raising your hands, somehow familiar with Bitcoin, but maybe less familiar with quantum computing. So you raised your hand if you are involved in Bitcoin since a while. How many of you are actually pretty familiar with quantum computing? One. Okay, so probably the choice was good, and so you are the one that I have to distract in order. You are the only one that can debunk me here. So I will try to keep an eye on you. So okay, let's go very fast over the Bitcoin part. You can read something, right? Even if it's the color choice is not perfect with the light, but is my, I don't know, it's my aesthetical fetish. I always do presentation with matrix colors. I cannot help it, sorry. I know it's not optimal, but I like it. Bitcoin uses cryptography, cryptocurrency. It doesn't use cryptography for encryption at all. It does use cryptography in other ways. The first kind of cryptography uses is a function, a hash function of the SHA-2 family, SHA-256, and it uses that for mining. Basically, the interesting thing about mining that is relevant for our conversation tonight is that mining, as a strategy, doesn't assume that the cryptographic function cannot be broken. It does assume that it can be broken in a nice way, because the point of mining is actually people brute forcing a cryptographic function. So it's not that you have to have a cryptographic function which is really sound. You have to have a cryptographic function that is easy to break, but at a controlled difficulty, which is the mining difficulty. We don't actually use SHA-256 only for mining, so for block creation. We use that also for P2SH or P2PKH addresses. Normal Bitcoin addresses, so addresses started with 1 are hashes of public keys, and addresses started with 3, they are hashes of scripts, basically. So we use the hash function there as well. Actually, 2 different hash functions, but okay. And in mining, it's a double round of SHA-256. And we actually use SHA also for the HTLC operation in the Lightning Network. So when you pay in Polis with the Lightning Network, what you are doing is you also create the hash of a secret, of a pre-image, in order to manage the security of the channel and of the routing of the payment. So people talks a lot about SHA-2 in the context of mining, but SHA-2 is also relevant in the context of Lightning Network. At least for now, we use the HTLC function. There are other options and other ideas. The uses are very different, because in mining, you don't have to find the exact hash. It's not that I give you a hash and I ask you, give me a pre-image that really hashes to this hash, because that would be very, very difficult. We just give you a difficulty. Give me any kind of pre-image that hashes to any kind of number which is below this difficulty threshold. So it's mining is an easier problem to brute force, while addresses and HTLCs are very hard problem, because I tell you, give me the pre-image that exactly hashes to this number, and not one more and not one less. Also, and this will be more important for tonight, in Bitcoin we use ACDSA, so the digital scheme algorithm for elliptic curve, which is basically a form of public key asymmetric cryptography based on elliptic curve over finite fields. Other than telling you how do we use cryptography in Bitcoin, I would like to recap very briefly, and later we will make use. Maybe I change the mic. This is better. I will make use of this point. I would like to recap some best practices in the Bitcoin security. The first one is that Bitcoin as a production, mission-critical, safety-critical system where life savings may be at stake, and when survival of people may be at stake, doesn't use experimental, fancy, newly discovered cryptographic function. You know that in the cryptographic community there is this mantra: don't roll out your own crypto, use stuff that is already tested, known. People say usually use something that survived at least 20 years of continuous attacking. Of course, that's a very high threshold, but it's a threshold that people in a production system, when you have to do with cryptography, people use that kind of threshold. If you think about that, for example, now there is a lot of discussion. We also did a presentation here about Schnorr signatures. Schnorr signature is another way to use, as a more simple, natural, and pretty and versatile way to use the elliptic curve cryptography. The same curve, actually, the same point, but use a different signature scheme, which is better. But Schnorr signatures were patented. There was a patent. And this patent expired just before Satoshi started to develop Bitcoin. And when Satoshi started to develop Bitcoin, Schnorr was patent-free, but it was not tested because nobody had the reason, the time, the incentives to test it because it was patented. So Satoshi instead used OpenSSL with the normal CDSA algorithm, which was not the best available back then, but it was the one which had more years of aggressive battlefield testing on his shoulders. So this point is important for the future. We don't use the fancy algorithm which we just discovered yesterday. We use something that was battle tested in production for a lot of time, in which we know the weaknesses, the conditions, we tested the assumptions, we have a lot of good implementations, we discovered the bugs of the implementation, we fixed the bugs, we have different implementation, we have hardware, we have secure elements, and so, and so, and so. The second point is that is about awareness of trade-offs. In Bitcoin, we can choose different cryptographic functions, but there are trade-offs in life, and sometimes we pick a function which is not the best function for something, because otherwise we will have to give up something else. For example, it's nice to use ring signatures in Monero, but you give up a lot of scalability because basically you have very big signatures. It's nice to use the ZK snarks based zero-knowledge proof in Zcash, but you create a transaction that are very big and very slow, and they basically create a problem with scalability. So you have a trade-off. And if you don't have a trade-off, of course, use the best function. But if you have to a trade-off, you have to be very, very careful to analyze what are you giving up in order to give what you are giving. So you cannot, there is not such a thing as a free lunch, right? If there was a free lunch, you have something better, you take it. But when you get something better, you have to first stop and ask what I am giving up in order to get this. And this is not a trivial question, especially in the discussion we will do tonight. And the last thing is that even if you have to change substantially some of the cryptographic functions, some of the architectural part of Bitcoin, and even if this change is super disruptive economically, so let's assume that spoiler alert for a second part of the talk. Let's assume that quantum computer, real quantum computers exist. They can break a CDSA, and we have to migrate to Lampport signatures. And when we do that, we cannot really fix all the public keys that are already exposed. And so basically, one single attacker takes over probably something like more than 20% of the money in Bitcoin, if not more, because in some scenarios they maybe could take over 60% of the money. So that's very, very bad. Still, this point here is that even the more economically disruptive scenario of any kind of migration in Bitcoin is still a better scenario than starting the economics from scratch right now without having the same condition that Satoshi had in 2008. My assumption is that if I create my scammy ICO now and my scam coin has the best cryptographic function, they work perfectly, no bug, no problem, I create it and now I sell you the token, or I start mining right now, of course, like you have seen in green, right, with venture capitals pre-accumulating GPU power to mine in advance to front-run the market. So if you start a scam coin now, the best scenario will be a worse scenario compared to the worst case scenario if we upgrade Bitcoin in a very bad way. Because anyway, we end up worse off as a distribution of money than a single actor taking 60% of the money, which is the worst case scenario. This is also kind of important, and now let's go to quantum computing. So as the guys here know, because I was not very social today, I decided to redo this presentation a lot today. I had a lot of cool explanations about quantum mechanics, but I decided that it was like probably 2 hours only that. So I decided to stay very, very, very superficial. If you have any kind of question about, you know something about quantum computing. Who does know something about quantum mechanics in general? Well, better, 5, which is better. So for everybody else, I will try to stay very, very superficial. If needed, we will drill down a little bit more. But don't worry, because as Richard Feynman said, I think I can safely say that nobody understands quantum mechanics. So even if you don't, nobody else does. So it's okay. It's safe. We can use this assumption. The first assumption is that very, very tiny systems can be in a state which is called of superposition. So I will use some very shallow examples. You toss a coin. When you measure a coin, it's either so you toss a coin. Let's see if I have one. Yes, I have one. So I toss it. Now it's either head or tail. I don't know which one, but even before I look at it, the coin will be in one of the two states, either head or tail. In a microsystem of quantum mechanics, that's not the case. Basically, until I go to actually look at the coin can be in a superposition state in which basically it is, let's say, half head or half tail, or 1/3 tail or two-third head, and it can stay in superposition. The second point is entanglement, which, to make it short, not just a single object can be in superposition, but also a very complex system can be in a coherent superposition in which actually, for example, let's say that I have two. Okay, you know about the poor Schrödinger cat. You know, sometimes he's alive, sometimes he's dead. Let's assume we have two cats, so we are doing like a cat carnage tonight. And so cat person. We have two cats in two boxes. We let down a little ball. The ball will either go left or right, and if it goes left, it kills the cat on the left. If it goes right, it kills the cat on the right. So not only in theory, assuming that's a non-perturbed coherent quantum system, both cats are in a superposition of states, alive and dead. But when you measure one cat and you see that he is alive, then that immediately changes the states of the other, which will be dead. So the big system is in a superposition altogether, not individually. So the system is not really divisible. It's not really. This is also a violation of the naive idea of locality. In science, we are used to the idea that if we look at the system here, we can really ignore anything happening far away, as long as it's far away enough. That's not really true. With Bell inequality, we know that we can have non-trivial non-locality effects, basically. The third point is about unitary operators. So when I have a system which can be big and complex and made of different objects in relationship among them, and this system I go to do stuff on it, to apply operators. Some operators behave nicely and they don't collapse the system, and they change the system maintaining the superposition state. So that means that I leave my ball down. The ball is 50% on the right, 50% of the left, and now I do some mathematical operation on the ball before I measure the destiny of the cat. And the last point is the non-unitary operator, so collapse or measurement. So at the end, when I will open the box, I will create a decoherence, and I will actually collapse the wave function, and I will have just one value. So measurement is not, I cannot measure the superposition. I can create the superposition. I can play with the superposition using unitary operators, but then when I measure, the superposition will collapse, and I will just get one result, either head or tail. I cannot see half and half, because my brain is not in a if it is in a superposition, I don't know that. So, so that's the point. Quantum mechanics was important for a lot of things, from superconductors to microchips so everything we do in computer today is somehow connected with quantum mechanics. So quantum computing is just computing. We cannot have this computer without quantum effect in superconductors. But specifically, when we talk about quantum computing, we talk about something that started from this sentence of the same guy that said before that nobody understands quantum mechanics. And he said in 1981, trying to find a computer simulation of physics seems to me to be an excellent program to follow out. And I'm not happy with all the analysis that go with just a classical theory, because nature isn't classical, damn it. And if you want to make a simulation of nature, not nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy. So the beginning of quantum mechanics was about people were using computers to simulate, for example, hydrogen atom or helium atom. And Feynman said, you're using something which is classical, so the computer, the digital computer, to simulate something which is quantum mechanical. Why? You have electronic components that can be already quantum mechanical, so don't try to simulate quantum mechanics with classical digit stuff. Okay, let's use this. But use directly something which is an underlying quantum mechanical mechanism. This was just a theoretical idea for physicists. Nobody cared, literally, until a guy named Shor. So Shor doesn't have anything to do with Schnorr. So Schnorr, S-C-H-O-R-R-R, it's a different elliptic curve signature scheme, which is better than CDSA, because the signatures are linear, so you can add up the signature, and Bitcoin may move to Schnorr in the next thought fork, or one of the next thought forks. It doesn't have anything to do with Shor. So what Shor discovered is basically this. So take, for example, RSA, which is, okay, it's an acronym for about 3 people, is the typical signature scheme based on the factorization of very big numbers by prime numbers. So you have a big number, multiplying 2 prime numbers to obtain their product is very easy. So you take 3 times 5, you get 15. That's very easy. But if I give you 15 and I ask you to calculate which prime numbers multiplied together give you 15, I mean, with 15, it's kind of easy, but with big numbers, even just 3-digit number, 4-digit numbers, it becomes very problematic pretty fast. So if you have a big enough number, to find the prime numbers that multiply together give you the big number, it's a hard problem in computer science. So you will need, your computer will need basically to try one, and then again, and then again, and then again, and then again. But then this short guy, well, let's stay here because this is too complex. This short guy basically understood that there is another way to solve this problem. Basically, if you find the period p of, so if you take a random number r, and you raise an r to the exponent of n, and you take the module of the result over n, so the module is, 10 module 5 is 5, because you know you do 1, 2, 3, 4, 5, and then you start again 1, 2, 3, 4, 5, etc. So if you do this, basically you have a periodicity. You come back to the same, yeah, I left out the 0, I know. You come back to the same number after a period. So finding a period P is equivalent to finding the numbers that multiply together create the big number. But it's not only equivalent, it's even more difficult if you want to try randomly. If you just try this P randomly, you will take even more time than if you were searching for the numbers directly. But there is a quantum magic. Basically, since the periodicity is a typical characteristic of a wave, since a microscopical quantum system is characterized by a wave probability amplitude wave, if you use the characteristic structure of the microscopic system as a wave, you can find the period even without trying out all the possibilities. So let's use an acoustic wave as an example, even if it's clearly different in some ways. Acoustic, you know, you pinch a guitar string, and what happens is that the guitar string will initially vibrate very disorderly, so you will have any kind of vibration, but then some kind of vibration, the ones that are multiple of the length of the string, they will bounce at the corners, and they will add up together, reinforcing each other, so that the wave of this frequency will go there and go back and reinforce the same wave more and more and more. While all the waves that are not an exact multiple of the or submultiple of the length of the string, they will cancel out each other eventually. So at the beginning, the movement of the string is very disordered, but after a while, all the ugly frequency will cancel out, and all the nice frequency will actually add up one to the other. So basically what you have is that some physical systems where you have a wave can basically reproduce what in a form of mathematics will be a Fourier analysis, basically. So you can get a frequency from a system because you cancel out all the frequencies. So if you do this, basically what you have is that a quantum computer using the wave of probability of the microsystem can actually, it cannot find the number of the multiplication, but it can find the periodicity of the function. And since Shor discovered that the periodicity of the function is a way to calculate very easily, if some of you is interested, this is the whole process. I will not go into detail, I will just read it super fast, so you can follow it, and everybody else will just trust me. So basically, classical step, so use a classical computer, use the greatest common divisor algorithm on n and r, where n is the number you are trying to factor, and r is a random positive integer less than n, and if the greatest common divisor of m and n is 1, continue. If you find the factor using the greatest common divisor, you have found the non-trivial factor, and you are done. Quantum step, find the period P of the module of r raised to the n, small n module large N for all values of n. You apply the Hadamard gate to create a quantum superposition, you implement the function into a quantum transform, you perform the quantum Fourier transform. Classical step, if the period P is odd, then you have to go back to step 1 and pick another random number. But if it's even, you can continue. Another classical step, you check that the module n of m elevated to, sorry, this is n, elevated to p half isn't 0. If it's not 0, you can continue, and basically you solve the greatest common denominator, and the answer is the number. So this seems complicated, but what I want you to understand is that there is just one tiny bit of quantum magic. Everything else is just classical computer. So you need a big computer to do everything at the beginning and anything at the end. You just use a computer to basically to try to find a period of vibration of a wave. That's all. So this is fun, except that basically Shor discovered that not only you can break pretty easily RSA algorithm using this function if you have a quantum computer that can that can actually perform that calculation. That's, as we will see, is a big if. But variants of this algorithm can be used also to break the problem of discrete logs, and both in the variants of Diffie-Hellman and elliptic curve discrete log. So ACDSA, which is the signature scheme used by Bitcoin, can be broken very, very fast by this kind of algorithm if you have a working quantum computer that can perform these three quantum operations that we said before. Because the reason is that they are the same problem, basically. There are different cases of the hidden subgroup problem for finite abelian groups. So nobody was interested in quantum mechanics except for physicists, in quantum computation, quantum computing, except for physicists in the 80s. But after Shor, everybody started to lose their mind, because now it's not just a theoretical toy for physicists. Now, whoever can really build this machine will be able to break all the public key cryptography which is implemented around the world. So, I mean, people can, Shor didn't even know about Bitcoin clearly, but it was already a big deal back then, because you can break a lot of stuff if you break public key encryption. There is another, Grover is another guy that found another optimization mechanism, which is, we will talk about that a little bit, but it's less interesting. Basically, Grover algorithm is basically a way to find it's like let's call it. Computation scientists will have an heart attack now, but let's call it like a database search optimization algorithm. When you have to find some combination, instead of for mining, for example, if you want to find the pre-image that fit for a certain difficulty, instead of 2 rise to 256, you can do 2 elevated to the square root of 256. So there is a quadratic efficiency for searching in a space, for example, for a Nash collision. This is also interesting, but way less interesting than Shor. So we have Shor that can break a CDSA, and we had Grover that can speed up a little bit SHA-2. Only speed up a little bit, quadratic speed. So, just for context, quadratic speed is less than the optimization, for example, that you had from GPU to CPU to GPU, from GPU to FPGA, from FPGA to ASICs. So mining already had a lot of exponential optimizations in this very step incremental evolution, and this will be not even as serious as the others. Now we have Shor proposing a number factorization, and there are people starting to build different kinds of quantum computers. Basically, there are two big differences. Quantum computer can be a general purpose universal quantum computer, so like programmable like a computer, or not. If it's not, it's called like adiabatic quantum computer, and it's not really a quantum computer. So in order to be super simple, you cannot do Shor breaking of a CDSA over a non-universal adiabatic quantum computer. So D-Wave by Google cannot use Shor algorithm to break quantum stuff, to break cryptographic stuff. It's not really a computer. It's more like a single-purpose physical analog instrument to do some kind of specific tasks. Also, you have some approaches to use super cold quantum qubits. Qubits, yeah, probably you read it on the press, but qubit is, in computer you have the bit, which is either 1 or 0. The qubit is a bit in a superposition of 1 and 0. Maybe there is some 0 and some 1. When you will measure the bit, it will be either 1 or 0. But before you measure it, it can be in between, and it can interact with other qubits and with the operation that you do on the qubits. So that's a qubit. And to build a qubit, you either create something which is close to the absolute zero temperature, significantly colder than outer space, or not. All the approaches so far for not has not shown to be very promising. So in the following presentation, I will stay with universal quantum computer at almost absolute zero temperature. These are types of quantum computers, and now let's talk about open problems, theoretical and practical. Theoretical and practical. Many people, you will especially people paid in order to study quantum computers for a kind of obvious conflict of interest, will tend sometimes to downplay the difficulties of quantum computing, and maybe they will try to represent the difficulties as merely implementation details, like engineering challenges, like, okay, this is solved, now this is only an engineering challenging, which is like to say, give me enough money and I can do it. Which is not always the case, because that's not actually true. We also have some kind of theoretical problems here that are not yet solved, and we don't even know if the solution is possible in theory. So I will try to analyze that a little bit. People right now assume that since some companies like Intel and some venture capitals funded startups managed to create quantum computers of a couple of qubits, or 5 qubits, or maybe 7 qubits, or 10 qubits, or 17 qubits, then now we just wait for the famous Moore's law. So we have this kind of computational power in the 70s in big computer, bigger as rooms, and then Moore's law basically started to reduce the size and increase the power, and so disk capacity went up with Moore's law, and bandwidth, which is not true actually, but okay, and computation power, which is not true anymore with the superconductor, but okay. So people has this tendency to think that since you can create something with 17 qubits, then to arrive to the more than tens of thousands of qubits needed to break the CDSA in a few decades, then you just need to wait, and technology will go the same pace that it did for normal computers. But that's not really the case, because there are some problems. The first problem is about scalability without the coherence. So I will not read you all this stuff, but I will just tell you this. When you add one computer chip to another computer chip, you do that and you're fine. Maybe you have to provide a good soldering. You have to provide maybe a good cooling system, but you can just add up, scale physically a classical computer. While you cannot, adding 70 bits on a processor or 700 is not that different. You just have to have better engineering. You just have to build the factory to build the chip. Here, that's not the case, because you have to keep all the qubits in a coherent state among them, which means that you have to keep everything at a temperature which is significantly colder than the outer space temperature, and you have to keep everything completely insulated by external magnetic fields, noise of every kind. Also, the bits will basically be close to a classical computer that will produce a lot of heat, and the heat will create the coherence. So going from 2 qubits to 17 is not as going from 17 to 19. This is an exponential hard problem to scale. Maybe not literally exponential, but an exponential-ish kind of problem, engineering speaking. So it's not that since these guys built this computer with this many qubits, they can just wait and scale over the kind of qubits needed to just break once a CDSA in several years, which will be in the tens of thousands of qubits. But actually it will be more, and now we will talk about why it will be more. So the first thing is scale. the fact that you have a few qubits doesn't mean that you will be able someday to build a lot of qubits. It may be physically impossible. It may be physically possible. It may be physically impossible to build a large quantum computer that doesn't have the coherence when subjected to thermal, magnetical, or other kind of noise from the environment, including heat created by the computation in the classical part. So the second point is error correction. This is very nasty because the point is that in classical computing, there are errors in the computer. And errors are managed by error correction algorithm that can basically prevent errors and keep the computer working. But in quantum computers, you cannot prevent errors using classical error correcting algorithm, because in order to do that, you will collapse the state of the system. So you will basically lose your superposition, and you will lose your quantum computing property. So you have to correct things without using the classical correction mechanism. If you don't do that, your qubits are qubits, but the results are basically they have a correlated noise, so they are statistically insignificant, and they don't help you to solve the problem. So this is a nice image from IBM research, and you can see that if you have 5 qubits, or 15 qubits, or 50 qubits, or 100, or 200 or 500 qubits, which is itself maybe not even possible physically to go there maintaining the coherence. But even if you go there maintaining the coherence, now we are kind of here, and maybe we are moving toward there, maybe. Even if you go there, you are not improving anyhow your capability to solve complex problem, because you don't have error correction. So the other axis, the other arrow, is this idea of error correction. So the theory goes like this. I cannot enter the quantum computation to correct the errors with classical error correction algorithm, but I can use a cluster of thousands of physical qubits, and if I take them all together, I will create one logical qubit that will behave like a qubit which error corrects himself. So you use basically, this is really improper, but this is really an abuse of language, but you use one qubit to correct the other qubit and so on. And so you cluster together thousands of qubits in order to create one logical qubit. So you can see that even if you have an error correction of 0.001, it still doesn't help very much. But then if you go to this level of error, then you can start, if you also increase the scale, then you can start to, these big blocks down there are the interesting parts where you can actually maybe try to break a CDSA or something like that. The thing is that right now, we don't know if this theory about error correction is possible. And there are some studies. This is one. I can give you the Prezi later, and you can search it. There are several studies that says that it may be possible, given 6 assumptions that we know are not true in physical reality, but maybe they are close enough to physical reality. Then it may be possible. This is the threshold theory. It may be possible, or not, or not, or not. Right now, the level of error corrector qubits is 0. So right now, when a company tells you, I have 5 qubits, these are physical qubits. I have 17 qubits. These are physical qubits, not error-corrected logical qubits. We have 0 convincing results in physical implementation about logical error corrections in qubits. So, I mean, first, we need one scientific breakthrough, which is how to scale qubits in very, very big numbers, in coherence. Then we have to do a breakthrough about how to actually correct errors, which we still don't know even if it's possible. When people say that they use quantum computing to break CDSA already, they basically factor the number 15. And the reason they factor the number 15 is that 15 is written in a particular way where every state is basically 1. And so they already knew which gates to use and which gates not to use. So they basically cheated. They never got to factor the number 21 yet. So it's not really something which is here. The third problem is, well, I will go fast in this. The third problem is clock time. These computers are not necessarily very fast, and to make them faster, you have to increase the energy. But if you increase the energy, you can create the coherence, and also you have to perform several measurements because the results are statistical. It's not that the result is this is your number p. The result is 1 over some multiple of p. So you have to try several times to get a result. And so when people made calculations about the timing of quantum computer, they sometimes forget to tell you that the timing, the clock of the system is not the same clock of a classical computer. It may be significantly slower, so it can change the time of the computation pretty much. The last point, no, it's not the last actually. There are still 3. There is quantum gates. So it's not just about qubits. Of course, we say that we have to prepare the states in qubits, the states of the system, for example, the states that we want to measure, and then we have to perform actions on them. And to perform this action, we need quantum gates, so the equivalent of the CPU, basically. And we are not talking of few components. We are talking about something like 10 to the power of 10 gates in order to do something like breaking an ACDSA. This is a pretty big number if you try to multiply it. This is very huge. Even if people can make very big computers with a lot of qubits, to do this number of quantum gates may prove physically impossible in our physical reality. Maybe not, but probably yes. So you also have a precision problem. This is also a wall of text, but I will try to say it that way. So how do you know which is the initial state of your qubit? In order to know that, for example, use a photon, a polarized photon, as a qubit. How do you know that, I mean, you want 1 qubit with a polarized photon, you have a laser, you polarize the photon, and you're okay. Now, you need 2 qubits. How do you know that they have been prepared in the same way, with basically the same kind of angle, down to a very, very high precision? It's difficult, but you can do that. How do you scale from that precision to thousands or tens of thousands of qubit precision? And how do you align your state qubit with the quantum gates? Because if they are not perfectly aligned, then your polarization will screw up inside the calculation. So this is something similar to the problem of analog computers. You know that before the advent of digital computers, many precision military or industrial environment, they were using analog computers. So they are computers, they can calculate stuff, but they don't use digital system, they use analog system, which can basically be faster because they can use a physical system to parallelize. So instead of putting there any single bit, you put there an entire system made, for example, the string of the guitar is great for analysis, for Fourier analysis, because digital Fourier analysis, you have to do very complicated integrals, while a guitar string is doing Fourier analysis for you, because it's a physical system built on a wave. So there is the same problem that people started to abandon analog computing, because even if it was faster to solve some kind of problem, it was very, very difficult to keep precise in input, in consistency of the internal, keeping the instrument precise enough was hell. So they moved to digital, where you lose all the nice parallelization property. And quantum computing, in a way, I know that this is a little bit improper because the number of states is way more than on an analog computer, but quantum computing, in principle, is not different to getting back to analog computing, in which you have very, very fast systems that perform some specific task faster in parallel, but you lose, you have to be super precise because you don't have error correction, and you have to be super precise in the input, in the gate management, and in the output measurement. So precise that, for example, for a 4,000 qubit computer, you have to basically manage to the power of 4,000 continuous variables. Consider that the number of protons in the universe is about 10 to 80. So the number of measurement variables you have to manage may be physically impossible with the kind of physical method that we use today to build stuff. Maybe we can use some kind of exotic particle lasers or stuff, but with the normal method that people are using right now in the laboratories of Intel to build the 17 qubits computer, this kind of precision over scale, at scale, may prove physically impossible. So this is challenging, right? Then the last thing is that economic incentives may be tricky. When you say Moore's law, you talk about the industry where computers started to produce results. So they were used in industry and in the armies and in wars. And so they produced result, and people started to invest more money to make them more precise and more small, more compact, more effective, more efficient. But there was an economical feedback loop of I put money, I create something that gives me some power, I earn money, and so I reinvest. The committee that was gathered, the U.S. National Academies of Science, Engineering, and Medicine about quantum mechanics was especially pointing quantum computing was especially pointing out that just last year that this kind of feedback loop may not exist in quantum mechanics because the amount of money that if the theoretical problem gets solved, because it's not sure that they get solved, the amount of money that you need may be too much, because before you arrive to quantum supremacy, which is the first cases in which a quantum computer is at least more efficient than a classical computer, before you arrive there, you need to spend a lot of money. And you don't get anything, because until you get there, you basically are wasting money. I mean, it's a very long-term investment. Something similar could be said with nuclear fusion. It's very nice if you have a nuclear fusion reactor, but in order to get there, you have to invest a lot of money with nothing in return, basically. And so basically they asked them if there is any significant chance to have quantum computers in the next 10 years. And they said no, there is no significant chance. And some of those people were working inside Intel's and Microsoft quantum computer research centers. And they say, no, there is not a significant chance of having these before 10 years. And of course, it's funny because you can read some newspaper accounting for the news. So the question is it possible? It's possible, everything is possible. Is it realistic, based on our knowledge, to get to this point before 10 years? Answer, no. Titles in the newspaper. Scientists say that we will have quantum computing after 10 years. So basically, if you really want to believe, you will believe. So before we go back to Bitcoin, just a general context and comparison. So after everything I said, it might look like we are just talking like snake oil. But a lot of things that we were not expecting in technology actually happened. So maybe all the results that I said, they may be impossible, they will prove possible. And maybe some new results will change all the premises. So this was a context to frame the situation in a realistic way. But maybe things will go differently. Things always go differently. So it's not impossible that we get a scary ACDSA breaking quantum computer in maybe a few years. But this is a list of things that I find personally, this is not a scientific opinion, but this is like I think it's a rational opinion, more probable than that. So this is not impossible, just improbable. And what I'm going to list now is something which is, in my opinion, a little more probable. The first thing is a swarm of self-replicating biological nano-ASICs. So basically, somebody started to tweak with biology and nanomechanics, and they create little organisms that are ASICs, and they break and they do hash collision for Bitcoin, and they self-replicate like bacteria, and they start to like eat CO2 hashing Bitcoin. This is physically possible. I mean, everything we know about nanomechanics is physically possible, and we were discussing biohacking. Biohacking materials in order to make them solve SHA-2 is physically possible based on everything we know. It may be an engineering problem, though, right? So there is something which is a little bit more, I think, more probable than this, which is solar-powered space pirates. So if you look at, on the internet about Peter Todd talk in Breaking Bitcoin 2017, or yeah, 2017 in Paris, Peter Todd, they gave a talk about solar-powered space pirates, a threat to Bitcoin. And he imagined the space technology advances enough that people start to put miners in a close orbit close to the sun and using solar energy in order to mine. So what are the implications for Bitcoin in terms of latency of the network? What if we are on the Earth? Do we need to decrease the block rate? Or what about the block size? He gave a serious talk about that, which is not super realistic, but still. I think I think personally a couple of orders of magnitude more realistic than quantum computers breaking a CDSA. And then I will give the most realistic one for me, which is still very, very realistic, which is low-cost nuclear fusion reactors that can change distribution of mining from hydropower in China to these big or small low-cost fusion reactors. I mean, maybe even cold fusion, right? Why not? I mean, yeah, that's theoretically impossible, but practically there's people that say that they did it. So who knows? So this is the context. I'm not saying this is impossible. I'm saying a lot of stuff is possible, and we cannot plan for everything unless we assign a probability to things and we look at trade-off and what we get up in order to get something in return. So let's talk about problems with countermeasures. So what are the possible countermeasures? Using post-quantum signature schemes. So there are some signature schemes that are not broken or not significant. They do not get significantly broken or significantly attacked by this kind of Shor algorithm in quantum computers. Of course, symmetric cryptography is not significantly affected. So, for example, most of the cryptography we use right now is public key cryptography only to move the symmetric key, and then we use the symmetric key a lot, and that's not really affected. Then there is like lattice-based cryptography, multivariate cryptography, chord-based cryptography, super singular elliptic curve isogeny cryptography, and hash-based cryptography, which the typical simple example is Lampport signatures, and a more complex example is XMSS. And I will not explain anything about all this stuff. I will just want to give you a quick flash about Lampport signatures because it's pretty neat. It's pretty. I mean, if you look at it, it's very simple to understand, and it's also very neat. So Lampport signature is based on only hash function. So your private key is a collection of couples of random numbers. So for example, this private key is a private key of three couples of 0 and 1. So the first couple is 0, 1. Sorry, it's a collection of a couple of random data. So random data, random data, random data, random data, random data, random data. The red dotted line is around the private key. Your private key is, in this case, a triplet of couples of random numbers. This is not a secure Lampport private key, of course. I'm using very small number in order to make it understandable. What is the public key? The public key is the hash of any single random data. So I take the first data, I hash it, and I publish it. I take the second, I hash it, and I publish it. The third, and so on, in the correct sequence. So I have six random numbers. I create 6 hashes, and I give up the hashes as the public key. Now, you give me a message to sign. For example, the message in this case is the message 001. It's a very simple binary message. So what I do, I take the first bit of the message, 0, and I use I reveal the first random data to number 0. So I take the second is still 0, so I again take the first random data in the second couple, but the third bit of the message is 1, and then in this case I reveal the second member of the couple for the third number. So basically what you can see in blue, you can see a very small blue dotted line. This is my signature, a collection of 3 random data numbers as the signatures. So everybody who has my public key can now see, so if I have the message and the public key and the signature, I can check that I added the private key, even if I don't know the private key. The problem with this is that it's a single use only. So use it once, and then you cannot, because otherwise with just 2 signatures, people can do brute forcing basically on my private key. But that's not so bad actually for Bitcoin. A lot of people are using more complex hash-based signatures for post-quantum cryptography because they want reusable signatures. So they use a Merkleized structure when you pre-commit to a Merkle tree. But in Bitcoin, the nice thing is that it's not too bad to have a one single-use signature because we don't want to reuse addresses. It's a bad policy to reuse addresses. So why not? Lampport is fine, and there are some evolution which are even more fine. What are the problems then? The problem for upgrade are basically these 3 problems. First problem are protocol updates in general. Updating Bitcoin, updating a decentralized system, which is permissionless and trustless and leaderless, is not easy. And if it's not really needed, it may not happen. You remember the SegWit problem. Now we will see the Schnorr soft fork 1 and the Schnorr soft fork 2. We will see how it goes. But it's not easy to upgrade a decentralized system. Of course, it's easy to upgrade a shitcoin because it's just 5 people in a room. They decide everything, and people will just download without update. But with an actual decentralized system, with money at stake, and with real developers discussing, the updates are not trivial to perform on the system. So any kind of change in Bitcoin is hard at the base layer, and it will become harder and harder in the future. So when we will have quantum threats, it may prove kind of hard to change the system. That said, if the quantum threat is deadly, then there is no problem, because the part of the system that will change will survive, and the part of the system that will not change will just die. So it may be an economic shock, but it's basically a Darwinian problem that solves itself. So it's better if you are in the part of the network that does the upgrade in that case. Upgrades are difficult. With SegWit, actually, they are less difficult. You can do a soft fork with SegWit versioning, script versioning, which is less disruptive, so it's easier to do. And so maybe we can have quantum resistant signature schemes that are not so difficult. The second problem is scalability. Lampport signatures are, as you have probably noticed from my super simple example, they are super huge, big, slow, bad signatures. We don't want them for scalability reasons. We will not upgrade to this kind of monsters if it's not strictly necessary, because they are absolutely bad for scalability. And the third problem is security. Security is an order of 3 problems. The first is theory. Not every idea you come up with is immediately secure. Maybe it's a good idea, but then people will try to break it, and maybe they break it even theoretically. There was a call from NIST for quantum resistant functions, and many of these quantum resistance functions that the people tried, a majority of them, they were quantum resistant, but they were not classical resistant. So you could not break them with a quantum computer, true, but you could break them with a normal computer. So this is not nice, right? There is a subclass of these signatures that are classical resistant and quantum resistant. For example, the hash-based signatures are provably safe. But the fact that they are theoretically safe doesn't mean that the implementations are safe. is not that if I find a mathematical paper describing an hash-based signature, then the code that implements the signature will be safe and bug-free at the first shot. Maybe there are bugs, and we don't know until we try to attack this stuff for years and years and years. For example, there is one of the reasons we had this presentation now is a debate now on Twitter. If you try if you write quantum computing, you will be basically assaulted by scam coiners selling their favorite quantum resistant scam coin. Is the new proof of stake, let's say. So they will promote coins using hash-based function that were proposed for the first time in 2013. This is not how security works. Even because, also because even if the algorithm is theoretically secure, in the case of this evoluted Lampport version, it is. And even if the implementation are secure, and that's, I will not really bet on that, then there is all the ecosystem, which means what hardware wallet are you using? I mean, in Bitcoin, you're using your hardware wallet with the secure element signing with the CDSA. Are there any hardware that can do the same with this hash-based stuff? Which kind of, practices do you use? You don't move to something new before it's safe in Bitcoin unless you are absolutely forced to. And as I tried to convey in the first part of my presentation, we are not really under an immediate threat of that kind. So these are the problems. And there is an urban legend that I would like to debunk at this point, and then I'm going to close. The urban legend is that Bitcoin is safe because we don't use public keys. We just use hashes of public keys or scripts, and so Bitcoin is fine. I was propagating this urban legend for a lot of time. I was going around saying exactly this, and recently there was a more serious analysis, especially by SIPA and by others, pointing out two problems. The first problem is not so serious. The first problem is front running. So your Bitcoins are not protected by public key, but by a hash. So when you spend, you move your Bitcoin to a quantum secure address, you reveal the public key only now and not before. And until you reveal the public key, the guys with the quantum computer, they cannot do anything. Little problem is that when you do reveal, they can try to front run you, basically cracking your public key on the fly, and try to to challenge you to come first in a block in order to take your money. This is especially realistic if you think that the guys, in the eventuality that we have realistic quantum computer, which I think is very, 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 very unlikely, then the guys with quantum computer may be miners because they have an advantage with, for Grover algorithm, they have a quadratic advantage in mining. So miners will probably have quantum computers. So if you sign your transactions and you show your public key, then miners will just take the public key and use the quantum computer to crack it and to sign a new transaction and to mine on the new transaction to take your money, especially if it's a lot of money. So this is not nice. This is not super. This is not a tragedy because we can use some kind of clever commitment scheme. So we can do a support that say that in order to spend a transaction, you have to insert the commit to the hash of that transaction inside another transaction done months before. Of course, there is a little problem of circularity because but it can work if you plan it carefully. So you can do an upgrade like that. But it's not true that having the hash itself protects your public key. The second problem, which is even more serious, was pointed out, I was talking about that at the beginning, and it's that most private keys in Bitcoin, probably for something which goes around the 60% or 40%, it depends on what you mean with compromise, but some public keys are, most of them are compromised. Some of them, like the guy that mined Bitcoin that may be Satoshi himself, 1.3 million Bitcoin in public keys without hash. And a lot of other people that reused the address, a lot of people reused the address, and everybody that reused the address exposed the public key. Some people expose the public key for multi-sig scheme, Lightning Network. In Lightning Network, we expose the keys a lot, and everybody exposing the XPub into Sentinel to create a watch-only wallet to check their cold wallet. They expose the public key to a server that maybe someday may leak the public key if there is a quantum computing threat. So this is second problem is serious. And how do you solve it? Either you ignore it, so you just allow the quantum computer guys to take over the money of other people, or you can blacklist the old addresses, which is something that will be a disaster from, I mean, let's think about the debate about blacklisting Satoshi's money. That will be nasty. So I hope we will never have this discussion. It will be bad. So this is probably the worst. The worst thing that will happen in the quantum computing scenario will be to have to decide if to blacklist or not expose public key. And also, what is the criteria of exposed? Only the paid to public key, or even the public key that were paid to public key hash that were later disclosed somewhere, or everything which is spent twice, or I mean, what's the criteria? It's pretty nasty, and I'm not even sure about what I think the account could be. So I'm going to close, and then maybe we take a break before the Q&A, right? I close with the last few slides. This is the strategic draft. So what do we do? I mean, the symbol I used like a flow chart, but it's not really a flow chart because it's more like a decision matrix. But I use this kind of graphics. So is it possible, in theory, to have a scalable quantum computer that can break a CDSA? If no, then relax, hodl, stack sets, eat meat, and life waits. Or don't, I don't care, but relax, that's the important part. If yes, then we go to the next question. If I was requested to give an estimation, I would say 90% no and 10% yes. Of course, this is just a random estimation, but I would say I will bet my money over no than yes because of the complexity we told about, error correction, scalability, time constraint, quantum gates. I mean, I will be more scared, a lot more scared by solar-powered space pirates. But assume that it is theoretically possible. Is it practical? So, is it practical enough that some agent, including a nation-state level agent, has the economic incentive to use that in order to crack Bitcoin instead of using it for something else, which is conditional to the first probability. So it exists, then I will give you 50% that is also practical. So I don't think it's theoretically possible. If it's theoretically possible, it may be practical during the life cycle of Bitcoin. So if it's practical in 30,000 after Christ, and maybe we move Bitcoin to a oh, yeah, so just quickly, there is something I didn't talk about. There is not only hash-based cryptography, there is also quantum cryptography. So quantum cryptography is not like post-quantum cryptography or quantum-resistant cryptography. Post-quantum cryptography or quantum-resistant cryptography is a form of cryptography that can resist a quantum attacker with Shor, for example. Quantum cryptography is a new science that uses quantum computing directly in order to perform cryptographic functions. So you can have quantum key distribution, etc., etc. The nice thing is that quantum cryptography is much easier to accomplish. It's still difficult, super difficult, but I think is orders of magnitude easier than quantum cryptography breaking. Quantum computing will advance, and it may bring us new functions based on quantum mechanics faster than it breaks the function, the classical function. So when I say it will be practical, what I mean is that even if it's theoretically possible, maybe it is practically possible after we already have a beautiful cryptographic solution may be based on quantum cryptography itself. So we don't know. I will give something like 50-50 that even if it's theoretically possible, it's still not practical because we have because the discussion is not relevant anymore. Either an asteroid destroyed the Earth, so who cares, or we just moved to another galaxy and block size is too big and we cannot synchronize the network, so we have to destroy the network anyway, or whatever. Or quantum computing is so advanced that we have new cryptographic functions. So if no, then again, relax, hodl, stack sets, admit, lift weights. If yes, so is it unevenly distributed? So does some people access quantum computer way before other people? So is like an academic research that everybody can follow and everybody, maybe somebody will arrive a little bit faster, like in ASICs, somebody arrived faster, but somebody arrived later, and eventually you may have some centralization, but eventually the market will take care of it and people will just build quantum computers. So the situation is this, so there is a nice distribution of this new power, or is this like super secret just in the NSA basement and now nobody else have it? So if the answer is no, it's not, it's uneven, then okay, we don't have to worry about mining, but we still have to worry about the CDSA, because even if everybody can break a CDSA, I mean, everybody can break a CDSA, so we should do something. We have a problem with Shor algorithm. And if it is uneven, then we have two problems. First, we have a problem with Grover algorithm because now NSA has a quadratic efficiency over any other miner. And then we also have to fix a CDSA. So maybe we have to do a proof of work change and also a signature scheme change. I don't know. I mean, this is very, very, very unlikely. Also, the reason, well, I will discuss that at the end of in 1 minute. It can happen that the distribution of something is uneven. For example, ASICS Boost, the cover version was done secretly by Bitmain, and they had an advantage over other mining producers, and they exploited the advantage. So this stuff can happen. It's not impossible. But I think it's really unrealistic, not very likely that you can build something like a real quantum computer in secret. After you do that, then you need the protocol upgrade. What is the protocol upgrade? The protocol upgrade, which is so 90% it doesn't happen. 10% it happen, 50% is not practical until it's already a dead problem. But if it happens, then I mean, I gave a very high probability to this, but let's think. The probability that I'm alive when this happens is still even lower. It could happen in 200 years. So protocol upgrade are basically the best current choice of signature scheme, which is not something we are studying now. It's something we will have to choose and pick then. It will be the best, the more, the smaller, the safer, the more practical, the more tested, the more implemented signature scheme when the shit hits the fan. The best upgrade path, for example, with front-running prevention, and the best theft mitigation path, which I don't know what it is because, as I said before, the problem of protecting all the addresses that don't move may be a very ugly problem to have. So this is it. I will just do a few last considerations. One is, what if there are not public clues of realistic developments? So what if the NSA, so everything I say to you is the public available research, but then there is a secret research in the basement of the NSA, or in the Area 51, where they actually did manage to build a CDSA breaker. It's extremely unlikely, because the kind of breakthrough that we need are mathematical breakthrough in order to do stuff like error correction, etc. This kind of breakthrough can, even if you kidnap, like in the Dr. Evil of Austin Power, he kidnaps the scientists and keep them in the basement. You cannot force scientists to have mathematical breakthroughs. Mathematical breakthroughs happen in decades of discussion among public discussion among mathematics, and you know that they are discussing about that. You need material breakthroughs, and when you have material breakthroughs in order to build big quantum computers or billions and billions and trillions of quantum gates, you know that because we are basically have spaceships going to Pluto every other week, because you have to change every kind of technological assumption we are using right now. So the idea that they are doing that in secret, nothing is impossible. But again, many things are way less impossible than this. And also there are, I mean, unknowns. Yes, some NSA can have like, maybe they have the magic powers with unicorns and wizards, we don't know. We cannot plan for something which is completely outside our predictability model. We can plan for, so we can plan for something completely unknown, but not with an actual countermeasure, because we don't know what we're talking about. So it's true that maybe I'm wrong, but maybe we are wrong about magic mutant ninja pirate unicorns in the basements of the NSA, and these unicorns are a more serious threat to Bitcoin. So the second question is, would uneven distribution to be the only problem with quantum mining? No, even if the distribution, even if the knowledge about quantum mining is widespread and evenly distributed, still quantum mining could be not great, because it may have a higher barrier to entry. So right now, to create a factory to print ASICs to compete with Bitmain and with other guys is pretty expensive. So there is a lot of barrier to competition. Maybe a quantum computer is worse as a barrier to competition. That's possible, and that's not a nice thing. And also there is this is a very nerdy problematic, but basically when you know that another miner discovered a block, you don't, so you can immediately interrupt what you're doing, and so I'm trying to discover the new block. So I'm trying hash collision. Then I get the other miner with a block, valid block. I stop, and I stop without having accomplished anything, because I didn't solve it, so I stop, and I have to move to the next block. But with quantum computing, I have my quantum computer running the Grover algorithm in coherent state. I wait because I have to wait. But now somebody else discovers a block. I will observe and collapse right now, and maybe I won. So there may be a higher orphan rate because of that. Because when I stop quantum mining, maybe I already won and I didn't even know. I will only look at that right now. So this could be not great. The last consideration, wouldn't centralized systems be just as affected? Oh, this is another thing that I wanted to debunk. Like, who cares if there is quantum cryptography, quantum cryptography breaking? Everything else will be affected, I mean everything. This is not exactly true, because most of centralized systems, first of all, rely heavily on symmetric cryptography, which is more resistant. Bitcoin is a system that relies heavily on public key asymmetric cryptography. That's not true for many, for example, military or banking grade systems. There is some use of public key cryptography, but it's not. They can use symmetric a lot, and also they have an easier upgrade path. If you want to upgrade the centralized system, you have a governance, and they decide, and you upgrade. You may have less problems of this kind of this kind. So the last question, and finally we take a break, is should we all invest in your classical quantum simulator startup? Yes, please. I will meet later to take your money. Thank you.
Giacomo, the first one is, of course, do you think the price of Bitcoin will go up or down?
Eventually up and first a little bit down.
Okay, but now the serious question. So suppose like some breakthrough comes, or like suppose it's possible to build quantum computer and break this cryptography. Like what would you consider the sign that now is the time to really start thinking about how to protect Bitcoin, how to upgrade, and so on? So because we want to do it before shit hits the fan, so there would be probably some kind of event that we could consider like now is the dangerous time, we should really work on it. So what do you think would be this kind of event?
So whenever you have, I would say, the science could be the first time somebody creates a new kind of engineering process out of nothing to have a scale, a quantum, a coherent set of thousands of qubits on scale. That would be a sign. This will not be like a mathematical paper about this kind of theoretical model of Shor. That will be an engineering, material engineering paper about we found a new way, completely different from traditional, to put tens of thousands of qubits in coherent state without interference, without any kind of decoherence. That will be the first sign. And I think that that will have to use some material technology that we don't even imagine right now. So something with big with huge waterfall effect over transportation and what else. The second will be the creation of the first reliable quantum corrected qubit or set of logic qubits. So when I see when somebody publish on a peer review and people can replicate a computer with a few of interacting quantum corrected logical qubits, then we are starting to get closer to the actual realization. And the third kind of thing will be basically some kind of mathematical breakthrough that can reduce the number of logical gates you need, the quantum gates that you need in order to perform. So we talked a lot about general purpose quantum computers. Actually, to break CDSA, you don't need that. You need also a specific purpose Shor optimized machine. So if you can optimize with fewer logical gates and not trillions, a machine for specifically Shor, then people will have to come out with a specific theoretical models. Before they can build it, they can imagine how to do it. Then they can create the technology to build it, and then they can solve the problem of error correction. Then maybe I will start to say, maybe we don't have to worry, but it's better to have a plan B. Right now, it's nice to speculate, but just as it's nice to speculate about everything else.
Thank you very much. So if anyone has a question, please. Okay.
Hey, so I was wondering about with the research thing part, so with R&D. So since, you know, private companies also rely on government funding to do the research into quantum computing, and especially as universities. So since, you know, hyper-Bitcoinization is just like 10 years away or 20 years away, don't you think that you know, when fiat currency gonna collapse, all the money that the government prints out, it's just gonna stop, and then it's pointless to talk about quantum computing because they're gonna put it on to like permanent hold for like 50 or 60 or 70 years more, and then it's just gonna restart it from there. Is like against it?
I think it makes sense. Not just government spending. So a lot of Bay research is made by government spending, and a lot of let's say, overhyped research is made with government spending for the simple reason that bureaucrats are easy to impress and they are not responsible because they use, I mean, you know, the saying, when you use your money for yourself, you're very aware of quality and price. When you use your money for somebody else, you're not so aware of the quality but of the price. When you use somebody else's money for you, you're aware of the quality but not so much of the price. When you use somebody else's money for somebody else, then you don't care of the price and you care of the quality. And that's a typical state bureaucrat. He doesn't care, but because it's not his money, it's not his result. It's just a bureaucrat. So bureaucrats are very easy to trick into into science fiction spending. And if you cut the government spending through hyper-Bitcoinization, so either reduction in money printing capability, I mean, they can print whatever they want, but it doesn't give them wealth because wealth moves outside fiat toward Bitcoin, or if you reduce taxation because basically following, spying on people and tracking financial movements becomes harder, and so confiscate money becomes also harder with Bitcoin. Then if you combine these effects and you have a reduction of spending, you may have a reduction in funding for a lot of theoretical research, which is sad for theoretical research, but I mean, everything in life has a opportunity cost. Of course, I would like, I was a physicist, I would like a lot of billions of dollars on theoretical physics, but I mean, either I use mine or somebody else may have other kind of priorities. So people will decide with their money. So there is a second point, though, which is not necessarily involving government as a spender, which is the creation of incentives to overinvest into technological hype. So one of the reasons there is this VC Silicon Valley culture of spending into dreams is, of course, because there is a lot of cool technology to build, but also because there is a lot of liquidity printed by the central banks and arriving in the market, and you have to defend yourself from the depreciation of cash, and you don't know where to go. Basically, the manipulation of interest rates is created in order to incentivize misinvestment. So there is a lot of misinvestment, and people is trying to invest in things because interest rates are manipulating into forcing people into invest in things. And part of that is creating the bubble of technological pseudo-scientific investments, which is affecting not just the crypto world, which is 99% bullshit, but also the normal startup world, which is also 92% bullshit, let's say. So I think that many VCs in a sound money regime would not invest money in something that is not as productive, which somebody could find it sad or scary because, I mean, who will think about the long-term hard problem, fundamental problems? But if you think about that, if you think back to ages in which the market, the society used the hard money, like under the gold standard or even before under gold and silver physical money, there were not investment bubbles like the venture capital one, but that didn't mean that there were not long-term planning and basic research. The other way around, in a way, the artificial manipulation of money creates the incentive to invest. So you want to invest, but it doesn't create low time preference. It does create high time preference. So people don't think in the long run, I think in the short run. So a lot of people want to invest in whatever, so they also invest in something that doesn't make much sense. But they don't want to invest for the long run. They want to invest for the short run. So even if there was less investment overall over science fiction, there will be probably more investment in sustainable fundamental research aimed to the very long run, because that was typically hard money does to society. It lowers the time preference of people.
Any other question?
Also, that I don't want to sound like anti-freedom, but don't you think that all these like doomsday scenarios, okay, someone breaks all the cryptography, actually overstate the importance of Bitcoin in the future world? Because really, if you have a computer that can do anything, like, why would you even care about some cryptocurrency, you know?
Oh, so that's a good question. I don't think we are overstating that that's one of the options I made in the final scheme. So when I say, is it practical, whatever. When I say, is this practical, what I mean is this practical, is it overcome by other events, and is it people with quantum computer actually using that for Bitcoin? So it may be that it doesn't make sense. It's not very realistic that it doesn't make sense, because Bitcoin is a bearer instrument with a market value and a very high plausible deniability. So any kind of exploit that was not profitable typically in a centralized environment becomes very profitable in Bitcoin, because you can get away with some form of money that you can then sell pretty easily. So let's say a lot of insider job exit scam that were not profitable before Bitcoin became profitable, because now you have this kind of money that a hacker will not attack a bank because they cannot run away with a bank account. But the same hacker will probably attack a Bitcoin exchange with the same vulnerability, the same cost, because the advantage of having some Bitcoin to run away with, to hide. Bitcoin is a dark market money, is easy to hide, easy to move, easy to send very far. It's a bearer instrument, not tied to an identity. So if you have a quantum computer, the opportunity cost of not using it for Bitcoin is kind of high, unless you have other, so you are in the NSA. If you attack Bitcoin, you lose your advantage over nuclear system and stuff like that. So that's a possible analysis scenario.
If your attack actually happens, and then you cannot really run away with Bitcoin, because everyone would know it was attacked and they lost their money. So, actually, all the Bitcoin, the value would be zero. No?
Why? You see, I target 3 of the most rich accounts, and I forge the CDSA signature, and I just move them, and I sold them, and sell them on the market, and then, the secret ACDSA breaker doesn't leave any trace. You just see a signature, which is a true signature. Maybe it's happening already.
Yeah, I have just, if you don't believe, Giacomo, that these post-quantum algorithms are easy to break, I have a recommendation for a talk to watch, which was by Dan Bernstein at the last year's CCC. And he's part of the standardization project for new quantum-resistant signature schemes. And it is very nice to display the names of the signature schemes in colors. So black was not broken yet, and red was completely broken, and it was 70% red. And it's like not, these algorithms, they are not invented by stupid people. These are cryptographers. And it's so easy to make mistakes that even, when they're trying to find a standard for a signature scheme, they're trying to develop it on a kind of existing mathematical schemes with known properties. And even so, they get it so wrong so many times. We're like totally nowhere near a really good signature algorithm that is quantum resistant. And those that have not been broken have either very large keys, very large signatures, usually both, and they're usually very slow. So they're not really good for Bitcoin, because of course you can have the hash-based signature which takes 70 kilobytes, but then the transaction would be pretty expensive in Bitcoin. And also you need to verify it fast, you need to be able to fit it in the block, and all the other things. So so it's not like what I like to do is when all these scam coins with new new signature schemes come out, I always check if the signature scheme has been attacked. And it's like usually, okay, they write a white paper, they start their ICO, and when the ICO is finished, the algorithm has already been broken. But they say, oh, no worries, we will upgrade, it was just in white paper. So it's it's this kind of race. So it's not, maybe someone will break elliptic curves cryptography in 10 years. It is like, they write the white paper, they didn't even start coding yet, and the signature scheme is already broken when even before. So I just wanted to kind of explain how really difficult this problem is. It's not, let's pick one of those cool signatures.
Absolutely, yeah. That's also my understanding. Most of the practical post-quantum algorithms are broken from a theoretical point of view, and some of them we don't know if they are, but they may be. Some of them are not, but they are impractical, just like the Lampport signatures and their evolution. So it's super difficult, and also, as we said before, there is a theoretical vulnerability, so that the scheme was considered by smart people, but there is a vulnerability, or there is a scheme which is solid, but still the implementation will be broken somehow, which is an entire new problem, which is multiplies, and the only way you have to face it is with time and with attacks and with defenses and with patches. And that's why I say that I think that the rational path for quantum resistance will be to ignore the scenario for now. I mean, ignore. You can work on it. You can have fun. You can produce research. Then when you have a realistic threat of quantum vulnerability of a CDSA, then you pick the best faring algorithm in terms of scalability, security, implementation, history, and stuff like that. So,
and it will be more clear in 10 years.
Exactly,
than now.
which one it is exactly. And maybe hash-based signatures, they are totally impractical now, but maybe with the technological constraint of 2055, when the first logical qubits will be created, I don't think so, but let's assume in 2055 the first logical qubits gets created, maybe the size of a Lampport signature or Lampport private key is not so critical for the technology for the bandwidth, and I don't know, but there are a lot of things we don't know.
Hey, you mentioned that we are still not sure if this quantum computing will ever work, and you said that you only believe that it's possible in 10%, and you also said that it's unlikely that in next 10-year window we will come up with this quantum thing. My question is it how likely it is that in this 10-year window we will know for sure that it won't ever work, like we are coming to that end?
In physics, unlike in mathematics, knowing stuff for sure never really happens. For example, we can have a loss of interest because stuff doesn't work. If it doesn't work for a while, people stop searching in it, and people will search for other fields more promising, and they will just move. So we don't have a proof that it doesn't work. So you can create the typical, spaceship engine using material from space and condensing it. That's a theoretical model that works in theory. In practice, practicality basically killed that in the previous studies, so nobody's working on that anymore, so it doesn't evolve anymore. So I don't think in 10 years we will see theoretical results of impossibility of doing that stuff. What we know is that it's probably possible without any kind of physical constraints, but there are physical constraints, and that makes it practically impossible unless we have some breakthroughs in material science, etc., etc., etc. So I think that in 10 years, my answer would be, probably in 10 years we will not have an impossibility result, but we will see clearly a burst of the hype. So the hype bubbles cannot be sustained forever. They have a tendency to grow. Typical academic bubble, there is a reason they last usually something like 30 years, for the reason that the guys that make a career in the bubble, they do not want to burst it until they finish the career, then they retire, and the new people, they don't have any interest in entering a field that is not producing any result, and they will just go hard into bashing the misconception of before. So there is a sociological cycle of academic bubble. Technological bubble are somehow faster than that, because there is more money at stake, not just people talking, there is more investments, and like press hype bubbles, they are super fast. If journalists cannot, journalists will teach, so you say something to a journalist, he will blow it up out of proportion. for 1 year, 2 years, maybe 5 years, and then they will have to move to some other kind of overhyped buzzword, because they have to feed something new to the public always, all the time.
Thanks, Giacomo, for your talk. I have a few questions. First is just what is the approximate number of qubits that you are talking about would be, or that could break the algorithms in the practical time, just to have a number in mind. Is it in thousands or tens of thousands?
It would be tens of thousands of logical qubits to break that in, I mean, it still will not be effective to break it on the fly by a miner, but you can break it in reasonable time in order to perform a reasonable attack. So actually, I think that is, no, tens of thousands is the number for RSA typical SHOR. I think the CDSA is a little bit smaller, but that's the order of magnitude.
Okay, just to have a number. Okay, the second question is, if the addresses of Satoshi would be broken and the money would be moved, you said we can deal with it by blacklisting these coins. What do you might see as a different strategies that we might apply?
So there are some, so this is a very bad strategy, of course, very problematic. There are, on the tip of my brain right now, I could think something which is still very, very ugly. But for example, when you move your coin, which are, for example, paid to public key, then there is like a public repository which is somehow distributed over, so far, let's assume it's centralized, then we find a way to decentralize. There is a onion site where you can update signed documents. So when you move a coin, which is paid to public key, the coin is not moved by the protocol for the amount of block of 3 months, and you have 3 months of time to sign this message, this standard message. If you sign that with the same signature, then he undoes the previous move, and then you have to find a way to move that again. So this is clearly ugly, but you can play a lot with, revocations of transactions, you can play with pre-commitments, but the great part of the problem is that if Satoshi had, I mean, I don't believe that these guys with this amount of Bitcoin, they just forget about checking if a quantum computer has been created. If the money doesn't move because it's either lost or inside the super deep storages with the technical difficulties. So any kind of way around it, it fails, because if Satoshi doesn't have the key, it doesn't have the key. So even if you create a system in which you can sign to revoke the theft transactions, it still cannot, because it doesn't have the keys. So it's not good also, because, I mean, if you allow this guy to find, so let's assume that this guy will also, so for example, people who lost the private keys, these Bitcoin are frozen forever, so thank you for the deflation. And this guy with the quantum computer arrives, and they will move them, re-putting them into the market. So it's also a little capped inflation attack in Bitcoin, which is ugly. So blacklisting may be the less ugly one, but I don't want to think about that.
Okay, let's just keep it theoretical. Okay, thank you very much for those. Thanks.
Any other questions?
Okay, so for my, oh yeah.
So is there any point to even just considering this whole quantum computing? Because it just seems like a for me.
The point is debunking a snake oil narrative. So the point of discussing this is understanding that there is no point discussing this yet.
Okay, thanks.
So are you saying I wasted my day? Thank you. Thank you.